Warning, tuning your vehicle can be a dangerous activity and there is substantial risk involved. The dangers include, but are not limited to, permanently damaging your vehicle, injury or death to yourself or other people, damaging personal property due to paying attention to a laptop while driving. This video is intended for educational purposes only. Before altering the calibration of your vehicle, you should verify it is in proper working and mechanical condition. Have a working basis of knowledge of how your vehicle works and how the components interrelate, and understand how your tuning software works. Bottom line, you and only you are responsible for making your own decisions, as well as accepting the consequences of those decisions. I cannot be held accountable for your actions. Welcome back, you pursuers of perfection, as we now get into part two, dealing with knock, which will turn your internal combustion engine into an infernal combustion engine. All right, so we're going to talk about knock tuning specifically as it relates to how GM has implemented this and as exposed by HP for us to do. So, the overall strategy is basically, as used by most tuners, is you were going to decrease the sensitivity of the knock sensors by raising the thresholds and make the recovery rate faster so that when knock occurs, we pull timing back out sooner and we defeat a few of the other knock strategies in place. The adaptive one, the burst knock, and the static retard. Then we're going to make sure that we are not being our own enemy and creating knock or encouraging knock by making sure our fueling is perfect, as well as investing time into making the high octane table as aggressive as possible, but not so aggressive as to cause knock. So when we go into HPTuners, you go into the Spark tab and you see the retard tab here, and we can see that we have four strategies. The first one is knock retard. This is the most simplistic one of all. Basically, it is triggered whenever the knock sensors are reporting that we have a problem, and it will pull timing out. And we'll discuss all of the values in here and what they do. The next one is the knock adaptive learning, and this is basically going to be serving as a backup to the knock retard section. So probably not accurate to think of it as long term and short term like fuel trims, but maybe think about knock retard as more of, hey, I'm responding in the moment, but if I get in trouble, I'm going to call in my big brother, which is this knock adaptive learning, which is going to serve as backup. Next, we have burst knock. And so this is actually triggered by transient throttle conditions, and it pulls timing out just in case. Just because, maybe we have a little bit of a sloppy tune from the factory. Maybe not sloppy tune, but maybe more like, hey, we have to weigh some real world consequences and balance things out. So we're going to pull timing out anyway, just in case. Maybe a knock happens, maybe doesn't. We're going to play it safe. And then next one, we have the static retard. And this is basically as baked in with the engine architecture, part selection. GM may have noticed that, hey, for some reason, this one cylinder always wants to knock while the other ones don't. So let's pull some timing out there just to be safe. And then finally, we have the maximum knock retard. And this is just a cap that overlooks everything to ensure that we're not pulling out too much timing. So before we go on, we will talk about the knock sensors. And there's a few things going on here. So we have these initial and minimum levels in here. And so this is going to establish the low end of the threshold. And these are millivolts, right? Knock sensors are essentially glorified microphones. A sound happens, it produces a voltage. The louder the sound, the louder the voltage. So in this case, we're saying the minimum threshold is 50 millivolts and the upper end is 120 millivolts. However, These multipliers down here, cylinder 1 through 8, this is used during static engine operations. In other words, not transient. And we'll talk about transient in a second. But otherwise, assumed steady state, if we're not meeting these conditions, each cylinder has a different set of multipliers based off of the spark air mass and the engine RPMs. And every cylinder is different, and part of that is due to the physical placement. You have two knock sensors, right? One on the drivers, one on the passengers in the middle of the block. So cylinders 3 and 5 are close, as well as cylinders 4 and 6. Those are the closest ones, right? So those thresholds are a little bit higher because they're closer. Sound has less material to go through, whereas the ones on the corners, what is that, 1, 2, 7, and 8, are going to have lower thresholds simply because there's more material to travel through. But either way, you can see that we have different multipliers. So the actual voltage, if we look at this, it says 5. Well, our low threshold is going to be 5 times 50, which is 250 millivolts. And then times 5 here, this is going to be, what, 600 approximately millivolts. So that would be our range if we were in fact multiplying by 5. Now, we also have a transient multiplier. So if these conditions are met, at least we have 0.04 grams of air mass. Our RPM is increasing or decreasing by this much, and TPS is increasing or decreasing by this much. We just have a simple multiplier across the board. All cylinders, all RPMs, we're going to multiply the thresholds by that much. We also have an EQ ratio multiplier. I think in general, you're going to find this is always set to 1 across the board. Um, but, maybe it would be interesting to think about. I don't know that I would want to do this, but, think about if we're commanding 0.85 lambda, so wide open throttle, typically 0.85 is used for NA motors. Maybe we would want to set the multiplier higher to pull out more spark. So if we get a little bit of detonation, that's probably the time to be a little bit more hyper reactive and pull it out. Just some food for thought. But what about for a lean cruise scenario, right? So, like in Australia, for instance, they have lean cruise. The US, we don't get it due to emissions, but a lean fuel mixture is more prone to detonate than a rich one. And so maybe we would be more cautious and want to set this multiplier higher than 1. Again, food for thought, just some things to think about. I don't know that I would necessarily do it, but maybe a jumping off point for you to experiment. Okay, so let's talk about each one of these systems more in depth. So our journey begins when the knock sensor threshold in millivoltage is exceeded. So we have a sound, it exceeds the threshold, and it kicks over here. First line of defense is knock retard. And so if we look at this max delta, this is basically saying we're going to allow an 8-degree spread of timing or knock being pulled out between different cylinders. Um, Disable time. This is interesting. So time, by the way, this is in crank pulses. This is not milliseconds or degrees or anything like that. But all this is saying is if burst knock is currently active and it is pulling timing out, and the knock sensor has said we have some activity, 0. We're waiting 0 crank pulses. In other words, immediately respond and pull out timing. So if this number is greater than 0, it's going to say, hey, if there's a transient condition, so you're moving the throttle, burst knock is active and doing, and that's key. Burst knock has to be active. Assuming it is active, it will say, okay, well, I need to wait this many crank pulses to deal with the knock sensor input. I would say you always want this to be 0. Even if you've disabled burst knock retard, you're going to want this to be 0. And I'll explain that in a little bit more in a second. And then max step, this is basically saying, hey, we can only pull out a maximum of 3 degrees. That's kind of our cap. We also have an amount table down here. And so you can see, and I believe this is a factory tune. Um, from GM, and you can see the smallest attack rate down here is 2.8 degrees and the largest is 3. So by the time you hit the engine coolant multiplier and the baro multiplier, probably all of these are going to exceed this maximum step of 3. But this will be interpolated from that initial and that minimum voltage level on the knock sensors. So it's not always going to pull 3. It's going to be somewhere between 0 and 3 based off of the knock sensor voltage interpolation on the thresholds. Then we have just the simple enable conditions. As long as these are higher than your normal engine RPMs, you'll be fine. And then we have a failure multiplier. So this is to say if a knock sensor goes bad or you have a short or otherwise, the ECM determines that we have a problem with the knock sensor and it throws a DTC, it's going to multiply all of this section by 0. In other words, if we can't trust the knock sensor, we probably shouldn't assume that we need to start pulling timing. So anything multiplied by 0 is 0 and the whole thing goes away. The next area is this recovery rate. And so this is again another really conservative area that GM has built in, and they're going to start. They're only going to very slowly start adding timing back in. So a safe thing to do would be to double this table. But again, like if you're getting a lot of knock, right, you need to address that. Okay, and you should probably be pretty conservative. So I don't want to say to go in and blindly double this. Use your judgment, but this is an area where these numbers should be bigger, most likely, if you've done your job properly tuning the car. As far as I know, these numbers are just coefficients into a larger equation. A bigger number is a bigger number, which timing is restored quicker. That how that equation works, I don't know, but just something to keep in mind. This max valid number, this apparently is part of an algorithm internal to the ECM that allows it to potentially determine false knock. So my assumption is that it it pulls timing, and if there is no reduction in what the knock sensors are saying, then it says, "Oh, well, I've tried pulling timing immediately and nothing happened, so I'm assuming that is false knock, and it will get rid of that." That's my assumption. I don't know how this exactly works. I would not recommend changing this. Whatever your factory value is, just leave it in there. It's made to work with your ECM. Okay, so now let's deal with the knock adaptive learning. So we have this up thresh or up threshold. And so basically this is going to say um, when we have exceeded, in this case, 1.5 degrees of knock retard, we're going to call in for help. And that's where knock retard calls in on knock adaptive learning. So we have this learn up threshold, and this is dealing with, there's a PID in the scanner you can log called the knock learn factor. And this is just a simple number that ranges from 0 to 1. 0 is what you want. 0 means I'm getting all my timing info from the high octane table. 1 is the worst condition, and that's saying I'm getting all my timing info from the low octane table. So zero point 0.5 then would interpolate halfway between the high and the low octane table. And that 0 through 1, I think, is the same on the Gen 5 as the Gen 4. 0 is what you want, but I think it's opposite on Gen 3, where Gen 3 is knock learn factor of 1 is high octane and 0 is low octane. Don't quote me on that, but I'm pretty sure that's how it is. So this learn up, I can't remember if I have the table. Oh, maybe before we do that, just understand this is one thing that it comes in my head and then I forget it. But if you fail the mass airflow sensor, the ECM by default, and it's only going to get its timing info from the low octane table. So if you go in speed density through failing the math, make sure you copy the high octane table to the low octane table so you get the proper timing. Um, so here's what happens, right? In this case, we exceed 1.5 degrees of knock retard over here, which is based on the amount and the multipliers. The learn up is then going to increment, in this case, 0.3. So if our knock learn factor is initially 0, in this case, any amount of timing that it's pulling out is going to increase it by zero point 0.3. Now, if we go back a few slides, this guy here, this learn down. Now, my operating system doesn't have it. Some of them do. This is going to be the opposite of learn up. And you can see there's just one value, but this is going to be how fast are we going to reduce the knock learn factor to go back to the high octane table. So um, again, a larger number will make it go back to the high octane faster. Oh, where were we? So in this case, our columns are degrees, 0 through 16. In this case, it's just flat lined across. 0.3 is going to be our increment of how we get up to or increase this knock learn factor. Yeah, I think we're ready to go. So just to drive it home a little bit clearer, if needed, we have two tables. We have this high octane table here. If the knock learn factor is 0, we get all of our timing info from high octane. If we're knock learn factor is 1, all of our timing info comes from low octane. If it's anywhere between 0 and 1, that's where we're interpolating high and low. So if we were in an operating condition where the high octane table says 40 degrees and the low octane table says 20 degrees, if our knock learn factor is 0.5, well, what's halfway between 20 and 40? That would be 30. So we would be commanding 30 degrees timing advance. All right, so first knock retard is a little bit complex, and this is one where I think most people, when they start tuning, this is going to be one of the first things they disable. It's a little bit aggressive. It can cause drivability issues. However, if you've done your due diligence in tuning the rest of the car, you should not have to worry about this. A lot of people will say burst knock is like predictive knock. I really don't like that term because predicting is saying, I'm, I'm pretty sure I'm more positive that we are going to knock than we aren't, that I'm going to pull timing. But to me, this is more like preemptive. In other words, it's saying we're entering a risky situation. I don't know if we're going to knock or not, but I'm going to tell you what, we're going to pull timing anyway. So most people, once they do the tune, they don't need this. And by that, I'm talking specifically about fueling. So get your mass airflow dialed in, get your virtual VE dialed in, handle transient fueling, and get rid of any power enrichment delay. The need for burst knock goes away. So the delay is, so when you get on the throttle, and that's going to be determined by this base versus cylinder air delta, wait 3 crank pulses. And if we meet everything, right, the whole time is going to be how long we are going to apply burst knock. So in this case, we will apply burst knock for 12 crank pulses. And then after that's done, the decay time is we'll bleed it back down to normal by the time 15 crank pulses are done. Now, base versus cylinder air delta. You can see that we have some operational modes, and then we have the grams of air in the cylinder, and then these are the degrees that we're going to pull out. This is pretty aggressive. I mean, less than half a gram of, wait, that's less half, not half. Half would be zero point 0.5. This is like 500ths of a gram of air, right? We're going to pull out 12 degrees of timing. That's pretty huge. So the way that most people defeat this is, well, really the only thing you can do is zero out this whole table. Now this goes back to what I was saying about this disable time. We do not have any rules in here that say only keep burst knock active if we meet these RPM conditions, engine coolant conditions, map conditions, whatever the case may be. This is always active. Now, if we zero out this table, guess what? Burst knock is still active. It's just whenever it goes to do something, it's 0. So if this disable time is set to something non-zero, it's going to wait for this to finish pulling out 0 degrees of timing before this activates and actually pulls out real knock from the sensors. So if you disable burst knock, it's going to be critical. This 0 needs to be in here for disable time. You can also see that we have some additional multipliers for RPM, coolant temp, and IAT that go into this as well. And that may desensitize it, knock it down from that 12 degrees value. There's also this burst learn in here, and there may be some more predictive type stuff. At the beginning, I was like, I don't like the predictive, it's more just preemptive kind of thing. Um, Again, what exactly these values control and how they work, and are you going to create yourself more problems than it's worth? I would just leave these alone. Your best bet, tune the car for real, zero this out, leave it alone. And then finally, we get to static retard. And this is where GM has gone in and they've said, hey, with this engine combination, this cam, this compression ratio, these heads, this piston, are we running premium fuel? Are we running on 87 octane fuel? Under these conditions, cylinder three always knocks. Don't know why, can't do anything about it. But at this timing, it's not happy. The other cylinders don't care. So you can see that they've kind of defined 0 through 7 or 1 through 8. Why they call it zero, I don't know. But you can see under these RPM conditions, we have both positive and negative numbers. So that's actually pretty cool. I'm assuming the negative numbers are actually adding advance, where the positive numbers are adding retard. So in this case, we're actually getting a little bit more performance. We're adding 3 degrees, so we should be making more power. So if you've done anything to internally modify the engine, dealing with the aforementioned uh, engine parts, zero this out. And then as you get knock, you're unfortunately just going to have to apply global changes on that high octane table. We're not going to be able to specify it unless you have some laboratory, clean room and you can test this out under all conditions. It's not feasible, right? Zero this thing out. So we have knock retard here. And this is just going to be a very general one that's going to be basically looking at three things. The knock retard, which is triggered from the knock sensors, the adaptive learning, which is going to be flexing between high and low octane tables, and then burst knock for transient throttle. There's another one called total knock retard, which includes all of those three, but it also includes the static retard value as well. Now, let's say you have a pretty much factory vehicle, meaning factory cam, heads, compression ratio, piston, and all of that. In that case, you'd want to keep that static retard that GM has defined. But as you go tuning the car and looking at the feedback from the scanner, you don't want static retard to be included as part of those numbers, right? You may look like, my gosh, it's pulling out 3 degrees of timing. I guess I have some knock going on. Let me pull 3 degrees out of the high octane table. Well, guess what? You're going to go drive again, and that static retard is still going to pull out 3 degrees. So, most likely, you shouldn't be using total knock retard if static retard is not zeroed out. In my situation, since I have a non-factory engine now, I've zeroed out static retard, but I do use total knock retard just to make sure that if there's anything in the background that I may or may not be aware of, I'm hoping that it will include it in there as well, just to cover all my bases. Otherwise, just use plain old knock retard. There are some other ones you may want. Probably just the regular knock learn factor would be sufficient. However, there is a knock learn factor for all 8 cylinders. There is a regular burst knock retard value, but there's also burst knock again for all 8 cylinders. So, as a starting point in your tuning journey, when you're first getting this sorted out, probably you're going to want to log all of these and then you can kind of scale them back over time as you get things squared away. Now, an important note, when we look at our high octane table, we can see the axes. We have RPM and we have spark air mass. Well, the timing table rows for spark air mass, we can't log spark air mass, but we can log cylinder air mass, which should be the same thing. However, how is cylinder air mass calculated? It's calculated from dynamic air. Okay, cool. Well, where does dynamic air come from? Dynamic air comes from a calculation based off of the mass airflow and the virtual VE tables. Okay. So, in other words, you got to get your airflow model sorted out properly in order for the spark air mass to be pulling in the right timing under different timing conditions. Right. So, don't be your own enemy and not dial in your airflow model because it's going to impact your spark. But more importantly, what underpins your airflow model is having the correct fuel injector characterization. You've got to have that fuel injector data to get your airflow model right, to get your spark air mass right. All right, enough of that. So, what do you do when you start seeing knock? So, first of all, situational awareness, just understanding of the knock retard strategies in place. Which one are you using? How do they work? And how do I dance around those things? So, you're going to want to test for false knock. And you're also going to make sure your tune is accurate. So, as I said before, transient fuel needs to be right. You have delayed power enrichment. In general, your airflow model needs to be right for MAF and VE. So, when you get knock, then you're going to want to test some things here. So, kind of in general, things to rule out and kind of the order that you want to go through is uh, attack maybe potential sources of false knock, meaning your knock sensors are picking up noise. Where's that noise coming from? It can be general things like loose exhaust, okay? Broken strut mount, broken motor mount, a heat shield that's rattling. All of those things are going to cause noises that can potentially resonate through the chassis or driveline and get picked up by the knock sensors. So make sure you don't have anything like that that's happening. And then mechanical issues, right? A bent push rod, broken rocker arm, broken valve spring, something like that. Anything that's causing a misfire. Maybe it's time for new plugs and wires. Those can all add noises as well. If possible, you could go to higher octane fuel, splash some more ethanol in there, or even juice it up with some type of octane booster, just to see if that causes the knock to go away. As a last thing, right? The last thing we want to do is reduce timing, right? Because that can just be a band-aid for other mechanical issues. So, and then if we reduce timing, guess what? If that doesn't solve it, then we probably need to desensitize the knock sensors. So if you can rule out false knock, then we go to the knock sensors. So it's going to be important when you log the knock retard, you're going to want to log it for each cylinder. And the reason I say that is because when you do, then you're going to be able to say, hey, under these conditions, it seems like cylinder three is always knocking. So if it's one cylinder, then there's a good chance that either something is mechanically wrong with that cylinder or potentially you need to decrease the knock sensors for that cylinder in that particular operating condition. Whereas if you look at it across the board and most of the cylinders or all of them are knocking, then a pretty good chance you have too much timing. So make sure you log knock for each cylinder. So when you set this up, you'll notice here is some kind of the way I have this particular example set up. We just have spark advance. We have knock retard, and that's basically everything but static, right? And then we have total knock retard, which includes static retard. First knock learn factor. Again, you can log the learn factor for each cylinder, but again, that only applies if you have that set up and are using it. Most people will defeat that. I think I forgot to mention that. They're going to defeat the knock learn factor by copying the high octane to the low octane table. So basically, it can't do anything. But the important part here is you're probably going to want to log knock for each of the 8 cylinders. I like to put the high value for 2. That way, with any slight change of knock coming in, we're going to see it. And then you're going to set up your axes the same as the high octane table with respect to RPM and cylinder air mass. When I do the total knock retard, HPTuners always wants to say, how about we use this generic sensor? So I always say, no, I know what I'm doing. Again, I do total knock because my static is zeroed out and I want to see everything just in case. So just FYI. Now, when you go into the actual chart here, by default, it's going to want to default to average. And I would say you probably don't want that to happen. You want to hit the plus sign to show the maximum value. So you can see the same log, we have vastly different results. So you can see, hey, I'm getting a degree pulled out in here. So we would need to investigate that if that's legit or false knock. So essentially, once you lower the high octane table, if you are still getting knock, then that's a pretty good indicator that it is false knock and you need to raise the knock sensor. On the other hand, if you reduce timing on high octane and the knock goes away, well, now you know that you had too much timing in there and you should leave it. So just be careful if you do a copy, paste, special, subtract directly from this table, you're going to get most likely some very jagged, ragged, peaky looking things in that chart that you don't want. So make sure that it is smooth for good transitions and you're not going to have weird herky-jerky power and torque going on. So just, be mindful, keep things smooth. Okay, so let's look at a transient knock scenario and let's just see kind of some things to look at as we go through this. So here is a log, and you can see this blue line here is going up, right? So we definitely are in a transient situation. We are increasing the air into the engine, RPMs are going up, and we have this little purple guy here that's pulling out 1.1 degrees. And so the thing that I'm looking for in a transient situation is this wideband. We can see that it is very flat. Like, sure, it has some ups and downs, but it's right at one, right? This is perfect. Couldn't ask for anything better. So if this is legit knock, I know it's not coming from fueling. It may be still too much timing, but I know tune-wise, I'm good. Well, through the magic of computer image editing software, let's just say this is what our fueling looks like from the wideband. So this red part is showing us, hey, we've actually gone lean during this throttle transition, and the wideband is showing a lean condition 1.2 lambda. So now all of a sudden, I would say, well, before I pull timing out, I should probably address this fueling issue. Looks like it could be a transient fueling related problem, so maybe I need to tackle that. So don't rule out fueling as a cause before you start pulling out timing. All right, so let's talk about the knock sensor threshold. So we've gone through everything, right? We've said, hey, we've done our false knock tests, and we're still getting some knock. We verified fueling is good. So now we actually need to increase that knock sensor threshold. So what most people will do is they're just going to go into this initial and the minimum level and they're going to multiply it, maybe 10% or so, maybe 20% if they're feeling frisky. And I would encourage you not to do that, but rather use these multipliers. And the reason why is because these levels are just blindly applying for all cylinders, all air masses, all RPMs, it's increasing it. So maybe we're on the verge. Maybe we'll just say 3,000 RPM at half a gram of air. We're commanding, I don't know, 40 degrees of timing. And the engine is almost ready to detonate. And it's wintertime, cold IATs. Well, now all of a sudden, we see false knock. So we just multiply this. And, the false knock goes away. And now we're happy. Few months go by, it's summertime, it's like 110 outside. Maybe there's some questionable fuel quality that we're in. And now all of a sudden, 3,000 RPMs at half a gram, 40 degrees is too much. And we are legitimately detonating. But because we raise these knock sensor thresholds higher to satisfy a different cylinder at a different operating condition, Now we're hiding the fact we don't know that we're doing that. So use these multipliers down here to address specific knock scenarios or false knock scenarios. Set these up. If you click on this table, you're going to see these RPM and these air mass definitions in here. So just set your axis up to match it and throw the knock retard for each cylinder. And then you can see the certain areas that you could copy, paste, multiply special into here. Now, you're probably going to want to multiply by more than 1%. So go slow. Don't just multiply the whole table by a lot, but you're going to have to figure out what works. But you can see we're going to target. This is a hot spot, right? This 3,000 RPMs in here at 0.4 grams. Maybe we need to desensitize it a little bit. So just one final thought on these thresholds here. So this initial level and min level are multiplied here, and that establishes our upper and our lower range or threshold. This is the area where we're going to interpolate how much knock we're going to pull out, that attack rate. So the idea is we want to set this lower bar high enough that we can get rid of all of the noise in the background that we don't care about so that when we get real detonation, we can pull timing. And you can see this is about, I don't know, 80% of this. So in this case, we would interpolate 80% of our maximum value based off of these thresholds. So that's everything. I hope you got something out of this and learned something, and this can help you on your journey for tuning. So see you next time, and more importantly, see you in the winner's circle. Later.